A coil in the shape of an equilateral triangle of side 0.01 meter is suspended from the vertex such that it is hanging in a vertical plane between pole pieces of permanent magnet, producing a horizontal magnetic field of 4 into 10 to the power minus 2 Tesla. If a current of 1 ampere is passing through it and the magnetic field is parallel to its plane, then the torque acting on the coil will be what? So we have to talk about the torque acting on current carrying loop. The loop is in the form of triangle suspended vertically and a horizontal constant or uniform magnetic field is present. Loop is carrying a current of I ampere. Now the net torque acting on current carrying loop will be given by magnetic moment of the loop, magnetic field, sine of theta. Magnetic moment can be given by n times current into area of the loop. Magnetic field, sine of 90 degree. Number of turns, n is 1 here. Current flowing is also 1 ampere. Area of equilateral triangle is given by under root 3 by 4 of side square, that is 0.01 square, or we can write 10 to the power minus 2 square, multiplied by magnetic field, that is 4 into 10 to the power minus 2 Tesla. So ultimately, after calculation, we will get the value of torque tau as 1.732 into 10 to the power minus of 6 Newton meter. And after looking the result, we can say that option number 4 is correct. Now let us move on to the next question, that is question number 7. Here is question number 7. A conducting rod AB of length L is rotated about point O with an angular velocity omega in a uniform magnetic field B0 directed perpendicular to the plane of rotation as shown in figure. Find the value of VB minus VA. You have to calculate VB minus VA, not VA minus VB. So this is the rod which is rotated with constant angular velocity omega about a point O. The lengths given L by 3 and 2L by 3. EMF will be induced and we have to calculate the difference of potential between point B and point A. In order to do that, let us consider a small element length dx located at a distance x from O. The speed of this dx can be written x into omega, like V equals R omega, so here x omega, and the small EMF induced due to the rotation of this small elemental length dx will be given by dV, that is VB into length of element, that is dx. V is already we have written x omega, magnetic field is B0 into dx. This is small EMF induced dV. Now the difference of potential between point B and point V, VB minus VA, will be given by integration of x omega B0 dx. Be very careful about the limit here. Point B can be taken as x equals 2L by 3 and point A will be at x equals minus L by 3. We have to take the integration from B to A. So the limit will be from 2L by 3 to minus of L by 3. Solving the integration, we get VB minus VA equals omega constant, magnetic field B0 constant comes out of the integration. Integration of x gives you x square upon 2, having the limit 2L by 3 to minus L by 3. Putting the limits, we get omega times B0, upper limit L square by 18 we get, minus of lower limit 4L square by 18 we get. Now after solving, ultimately we get the potential difference VB minus VA as minus of 1 by 6 B naught omega times L square. So after looking the answer that we have got, we can say that option number 1 is absolutely correct. So we will go with option number 1. Now let us proceed to the next question, that is question number 8. Question number 8. A rod PQ of length 1.25 meter is moving with velocity 10 meter per second on a parallel track placed in a uniform magnetic field B naught of 10 to the power minus 2 Tesla as shown in figure. If the total resistance of ABCDA loop is 10 square ohm, then find out the current through the loop at that instant. Now, this is an example of motional EMF. The induced EMF E may be given as V, B, L, and hence the induced current may be given by V, B, L divided by R, where V is velocity, B is magnetic field, and L is effective length of the rod. Here, the effective length is 1 meter. So putting the values, we get value of electric current E as velocity 10, magnetic field 10 to the power minus 2 into length of the rod, that is 1, whole divided by resistance, that is 10 to the power 2. So after solving, we'll get the value of current as 10 to the power minus 3 ampere or 1 milliampere. So we will go with option number 1. Now let us proceed to the next question, that is question number 9. Which one of the following is not considered as element of Earth's magnetic field? We know very well that there are 3 elements of Earth's magnetic field: angle of declination, angle of dip, and horizontal component of Earth's magnetic field. So let us go for the options. Vertical component of Earth's magnetic field. No. Earth's magnetic field has only 3 components, and vertical component of Earth's magnetic field is not element of Earth's magnetism or Earth's magnetic field. So we will go with this option. Option number 2, horizontal component. Yes, this is the element of Earth's magnetic field. Option number 3, angle of dip. Yes, this is also element of Earth's magnetic field. Fourth one is also an element of Earth's magnetic field. So we can say that we will go with option number 1. Now let us proceed to the next question, that is question number 10. A short bar magnet having magnetic moment M equals 0.80 joule per Tesla is placed in a uniform magnetic field of 0.30 Tesla. If the bar magnet is free to rotate in the plane of the field, where U is potential energy and tau is torque, then pick out the correct option. We know that potential energy stored in a bar magnet after rotating it by an angle theta will be given by negative of vector m dot vector b. In other words, minus of m b cos of theta. For stable equilibrium, theta gets 0. So that's why U will be equal to minus of mb cos 0, that is minus of m 0.80 multiplied by magnetic field 0.30 multiplied by cos of 0 degree, which gives you U equals minus of 0.24 joule. And since it is in equilibrium, so torque must be 0 here. In case of unstable equilibrium, theta gets value 180 degree. As a result, potential energy will be directly m into b. Putting the values, we will get plus of 0.24 joule as the potential energy stored. And since it is in equilibrium, so that's why we can say that tau here will also be 0. After getting the things, Now let us find out the options. Option number 1, for stable equilibrium U equals, no, it is given as plus of 0.24, which is incorrect. Option number 2, stable equilibrium U equals to 0.24, again incorrect. For stable equilibrium U equals minus of 0.24 joule and tau equals 0. This is absolutely correct. So we will go with option number 3.